So hi everyone, my name is Shtub and I'm head of training at ScyllaDB. And the topic of this talk is NoSQL basics and getting started with NoSQL. So just to make sure you're with me, if everybody can in the chat window write your location, where you are, and what you're drinking right now, if you're drinking anything. So I'm in Israel, in Tel Aviv, and I'm drinking some tea. Just in the chat window, so I see that I'm not talking to myself. Where you are and what are you drinking? Okay, I see some people from Israel. Okay, thank you for that. So this is me. As I've said, I'm head of training at ScyllaDB. I lead the training. My background is as a software engineer, and I'm based in Israel. The agenda for today, I will start with an overview of NoSQL, also called NoSQL, and ScyllaDB. And then I will talk about the architecture, some basic data modeling, the read and the write path, which are quite similar. And I want to leave some time for questions and also do some hands-on labs. So I will run the labs, and afterwards I will share the links with you so you can run the labs on your own. Yeah, throughout this talk, I want it to be as interactive as possible, so feel free to interrupt me, ask questions in the chat window. I will keep it open so I can see. Tell me if I'm going too fast or too slow, and let's try to keep it as interactive as possible. Great, so I will start with NoSQL and the overview of ScyllaDB. NoSQL, I guess most of you heard about it as opposed to the typical type of database that used to be the default or most common one. As the amount of data grew and also databases became distributed with a need for high performance, NoSQL began around 2000, and now there are quite a few NoSQL databases. And what you see here in this slide is the CAP theorem, which talks about distributed databases in general. Just a second, I lost my slides. Sorry, just a second. Okay. Can you see the slides again? Okay. So I was talking about the CAP theorem. And the CAP theorem is about distributed databases in general. So it's not just about NoSQL databases, it's about distributed databases. And it says that in distributed databases, we have three attributes we would like to strive for, and they are consistency, availability, and partition tolerance. However, there is a trade-off between them, and we have to pick two out of the three. And maybe in one sentence what they mean. So consistency, there are different ways to define it, but basically it means that for every read to our database, we would get the latest write. Availability means that for every query, we would get an answer. Not necessarily the correct answer, but we would get some answer. That's availability. And partition tolerance means that even if there's a network failure or some kind of network split, our database would still be able to serve requests. And there are dozens of database solutions out there. So I just picked a few and put them here where they stand according to the CAP theorem. So for example, we can see that ScyllaDB together with Cassandra, Apache Cassandra, and Amazon DynamoDB give a preference for availability over consistency, whereas some other databases like MongoDB have a preference for consistency over availability. So this is one way to look at NoSQL databases. Another way would be according to the data model. So here in this slide, we can see the data model ordered according to complexity. Okay, and the easiest or least complex data model would be key value stores. Some examples, there are more, are RocksDB, Aerospike, and Redis. And key value is as simple as it sounds. We have a key and a value, no need for any fancy query language. It's very easy to understand and very easy to data model. Next, in terms of complexity, we have document stores. And here we have, as an example, MongoDB and Couchbase. Document stores order the data or store the data in a structured manner. Think about XML or JSON, for example. And here we have tags that define some kind of structure for our data. Next, in terms of complexity, we have wide column stores. And here you can think about the data structured as tables. And some examples here are, again, ScyllaDB, Apache Cassandra, Amazon DynamoDB, and some others. And maybe the most complex data model would be graph databases. Some examples are Janus Graph and Neo4j. They are some popular ones. And here data is modeled according to edges and vertices, so as a graph. Just a second, I can't see the chat window, and I want to see if anyone has any questions. Let me restart the meeting. Okay. Okay, I see you're not even seeing my slides. Sorry about that. So let me reshare my screen. And open the chat window. Can you see the slides now? Let me
Yes, yeah, we
enlarge
can see
them. Okay, sorry about that. Present them. Okay, so it was hard to understand without the slides. Again, sorry. This is the CAP theorem, availability, consistency, and partition tolerance. Again, we have to pick 2 out of the 3. There's a trade-off, and I put some databases according to their preference. Next, this is the slide I talked about, the data model and the complexity. So key value, document store, wide column store, and graph ordered according to complexity. And next, I will talk about some attributes of ScyllaDB. So ScyllaDB is an open source NoSQL database. The examples that I will show you today are based on ScyllaDB. However, they are correct and relevant for some other databases, such as Apache Cassandra and Amazon DynamoDB, as well as some others. ScyllaDB was initially it started as a drop-in replacement for Apache Cassandra. Apache Cassandra is one of the top 10 leading databases, so it's quite popular. It was initially started at Facebook, and then it was open sourced. And ScyllaDB basically started as a rewrite of Apache Cassandra, which is written in Java, but with some performance and other improvements, and also written in C++. So some of the attributes of ScyllaDB are high availability. As I mentioned, it's built with high availability in mind, meaning that even if it's a distributed databases, even if some of our nodes or servers become unavailable, we can still serve requests. Scalability, again, it's distributed, and the database can run on multiple servers or nodes. So we have anywhere from 3 nodes all the way to hundreds of nodes running the same database. And that scalability means that if we require extra performance, we can simply add more nodes as the system is running without any downtime. And that also goes, again, together with high availability, meaning that there's redundancy in the system. Even if a node is down, other nodes can still serve requests. Performance, so we're talking about queries that can be performed in just a few milliseconds. Okay, so it's very, very highly performant. Also in terms of the latency and also in terms of the throughput. Okay. Low maintenance. So one of the pain points for Apache Cassandra was that it was a lot of effort to tune the system, things like garbage collection and tuning it and other things that needed to be done in Cassandra. So a lot of the effort by users was used for tuning the system. With ScyllaDB, that is not relevant, and the system has many auto-tuning features. And as I mentioned, ScyllaDB is a drop-in replacement for Apache Cassandra and for Amazon DynamoDB. So if a company is using Apache Cassandra as their database, they could simply keep their application and as it is and switch the underlying database to ScyllaDB and get all kinds of different benefits. So I don't want to go into the details of this slide, but these are just some examples from customers that migrated from different databases to ScyllaDB. And we can see that they reduced the number of nodes. Let's look at this Cassandra versus ScyllaDB example. So from 40 Cassandra nodes, they changed to 4 ScyllaDB nodes. They reduced the cost by 2.5 times and got 22 times better latencies. Okay, so it's easy to understand why it makes the effort of switching worthwhile. ScyllaDB comes in 3 different flavors. I mentioned it's open source software. You can see the code on GitHub. I put the link here, and by the way, we will share the slides with you by email after this talk, so you don't have to write down or copy anything or anything like that. The second option is ScyllaDB Enterprise, which is based on the open source version, but it comes with different extra features and also our 24/7 support. So for companies like banks or other companies that are that require mission critical support and they're running in production, that's a good option. And last but not least is our database as a service offering. So ScyllaDB Cloud is becoming more and more popular for companies that don't really want to deal with administrating a database, and they just want to focus on their core business, which is probably developing some kind of application. They get the database as a service, and we take care of running the database for you, upgrades, performance, security, backups, repairs, and everything like that. Again, of course, with support. I want to talk about 2 different resources that are available to you. I mentioned that I will send the slides with the links to you by email after this talk. One resource is called ScyllaDB University. It's our online learning and training resource center. You have quite a lot of material there, videos, hands-on labs, slides, and so on. It's completely free and it's self-paced. So all you need to do is create a user and start learning. So that's something I recommend you check out. And the second one is our documentation. So if I touch on a topic and we only have less than an hour, so I can't cover everything, you can simply look at our documentation and see the entire procedure, details, and so on about how to do different things. Maybe just one anecdote from one of our users. So Kiwi is a, I believe, flight search engine, and they are one of our customers. And they are using ScyllaDB. There was, I think 2 or 3 years ago, a fire in a big data center in Strasbourg. There was simply a fire and all the computers were burnt. And a lot of websites that were running on that data center, databases and websites became unavailable. However, because Kiwi was using ScyllaDB at multiple data centers, data was replicated. So they had no downtime at all. Even though a data center went down, which is unusual and very exceptional, their search engine stayed up and their users were able to still search for flights because other data centers were able to serve those requests. And I think that's quite amazing. Okay. With that, I've been talking for quite a lot. I want to show you a quick hands-on lab, and I'm going to show it to you. And like I said, later you can run it on your own. So I'm going to be using a platform called Killer Coda, and what this does is it runs a virtual machine within the browser. Again, you can see what I'm doing now, and later you can do it yourself. So what I did here is I started a single Scylla node running this Docker command. Okay, I just did it before we started, not to waste your time, as I download some files. And what this does is it starts a Docker instance with ScyllaDB and a node called ScyllaU. And once that starts, we can check the status of our node. There's a command called node_tool_status, and it shows me that my node is up and running. So we have a single ScyllaDB instance ready. And I can connect to that instance using something called the CQL shell. And I'm going to explain all these terms in just a bit, but I just want to show you how it works very quickly. So I connect to this node that I just created with a CQL shell. And moving forward, I create a key space. A key space is basically a collection of tables. Once I have my key space ready, is it ready? I can, using that key space, stuck for some reason. Okay, using my key space that I just created, I create a table. I call it users, and it has 3 columns. They are the user ID, the user's first name, and the user's last name. I define the primary key as the user ID. And now that I have this table ready, I can insert some data into my newly created table using the CQL command insert, and I insert into the table 2 rows with Rick Sanchez and Rust Cole. And once that happens, so because we're using a virtual machine, there is some lag. This is unusual. But once the data is inserted, I can simply read that data, select star from users, and that will show me the newly created table with the 2 rows in it. Okay, so that's how simple it is to start a Scylla cluster, write some data, and read that data. Okay, there you see the 2 rows that we just inserted. Okay, now let's understand what was happening behind the scenes. Okay, so let me talk about the architecture. And again, I'm going to talk about ScyllaDB, but whatever I'm saying is relevant for Apache Cassandra, most of it for DynamoDB, as well as other databases, NoSQL databases. Okay, so I kept saying node. There are many nodes, but I didn't say what a node is. So a node is basically the ScyllaDB software running on a machine, on a server. That's a node. A node consists of many shards. Basically, a shard, we think about it as a CPU. And each node contains a portion of the database content. Okay, so I mentioned that ScyllaDB is distributed. In a production system, we have to have at least 3 nodes, and we can have all the way to hundreds of nodes. So each one of the nodes is responsible for a part of our data. Okay, in ScyllaDB, again, in Apache Cassandra, all nodes are created equal. Okay, we don't have the concept of leader nodes or master slave nodes or whatever name you want to call it. All nodes are equal. All nodes can serve requests, and that goes together with the idea of high availability. So there's no single point of failure. Even if one node becomes unavailable, the other nodes can still serve requests. Okay, the next concept is called a cluster. A cluster is a collection of nodes that work together. Conceptually, we think about it as a node ring, okay? And as I've said, in production, we want to have at least 3 nodes, and depending on our workloads and use case, we can have hundreds of nodes. Maybe I'll just mention, going back to this slide, that all the communication is done with something called gossip, which is the internode communication. And again, the nodes communicate between themselves. So that means, again, that there's no single point of failure. There's no single node that concentrates all the communication or anything like that. They can all communicate among themselves. Okay, partition key. So when I created the table in the small demo that I showed you, I said that our user ID was the partition key. And what does that mean? So the way that ScyllaDB partitions data is as follows. For each table, we have a column that's defined as the partition key. It can be either 1 or more columns. And what the database does when we perform a read or a write query is it performs a consistent hash function on the value of the partition key. And according to the given hash, it knows which node is responsible for that piece of data. Okay, so here in this example, we have just 3 nodes in our cluster X, Y, Z. And if we take this specific column with ID 655AE or whatever, and we write that to the database, then the database, it's not something you have to do as a user, but under the hood, the database would partition that data. It would run the hash function on the value of the partition key 655AE and know which nodes are responsible for this piece of data. And how does that work? So each node in our 3-node cluster is responsible for a range of tokens. Okay, so this is a simplified example, but say we have a range of 1 to 400, 401 to 800, and 800 and more. So each node knows that it's responsible for these specific tokens. And according to the hash, we would know which node is responsible for this piece of data. Now, data replication is an important concept, and in ScyllaDB, data is replicated. That means that each piece of data is copied or replicated multiple times to different nodes, okay? And that is determined by something called the replication factor, also abbreviated as RF. And the replication factor is something that the user defines, okay? So the user of the database would define it according to the use case. And the replication factor is the number of nodes where data is replicated, okay? This is done automatically. So as a user, once you define the replication factor, you don't have to worry about data being replicated. And you define it per key space. So let's say, just for example, that I define a replication factor of 2, RF equals 2, and I have 3 nodes in my cluster. That means that each row of data that I have is going to be duplicated twice, and each copy is going to be stored on a different node, okay? And again, that goes together with high availability, because if I have 3 nodes and my data is replicated twice to 2 different nodes, that means that even if one node goes down, I could still serve requests because 2 nodes are still available, and one of them would still store my data. Okay, so that's the replication factor, and it's defined per key space. And it's easy to understand that if we, there's a trade-off here. So if we set a high replication factor, it would require more hardware, and that has a cost implication, but it would also give us a higher availability. Okay, so we might want to define different key spaces with different replication factors according to our specific requirements for the application. And I will talk a bit more about that when I talk about data modeling.
Scylla נחשב eventually consistent?
Ken, so I think there are also English speakers here. And the question was,
I'm sorry, yes.
The question was, is Scylla eventually consistent? And the answer is yes. It's considered eventually consistent, even though out of scope for this talk, we also use a protocol called Raft. And slowly we're moving more and more queries and functions to use Raft, which would mean that you can get strong consistency and not just eventual consistency. But that's more advanced for this talk at least. Okay, next concept is consistency level, also called CL. And consistency level is the number of nodes that must acknowledge a read or a write request. Some examples for values are 1, or quorum, or all. And the consistency level is defined per query, okay? So I can define that, say for a specific write query, my consistency level is all, meaning that all replicas must acknowledge this write. And maybe for a read request, that read request requires less consistency. So I can define that for that query, the consistency level is only 1. Okay, maybe an example to help make it more clear. So let's say that I have a 3-node cluster. My replication factor, as before, is defined as 2. And that means that each piece of data is copied to 2 different nodes or 2 different replicas. If I define my consistency level, to be all, that means that 2 replicas, because we have just 2 replicas, 2 replicas need to acknowledge that query. Okay, so Again, there's a trade-off between consistency and availability. If one of my replica nodes is down or unavailable for whatever reason, then that query will fail, okay? However, if I define the consistency level as 1, and we have one node down and one available, then that exact same query would succeed. And as I mentioned, tunable consistency, the consistency level is set per operation and per query. Okay, data centers. So I mentioned the fire in this data center in Strasbourg. ScyllaDB, again, as well as Apache Cassandra and DynamoDB, work with multiple data centers, and they're topology aware, meaning they know about the topology of the different data centers, including racks within the data center. So we can have ScyllaDB run a single cluster on multiple data centers, okay? And that makes sense for a number of reasons. One, the first one that comes to mind is availability. So if I have a data center in the US and say one in Asia, and there's a fire in the US one, the database would still be up and running and serving requests. It would just do so from the Asia data center. And once the US data center goes back up again, then the Asia data center could stream the data to the US data center and update it with whatever it missed when it was down. And all this is transparent both to the user and mostly to you as somebody that's administering the database, okay?
So in this example, if I set a replication factor of 3, will it be smart enough to replicate it across the different data centers, or will it stay within the ring in each?
So that depends on you. There is something called quorum and local quorum. So you can define that it would replicate across data centers or within a specific data center. Okay. But that's something that you can do. Okay, so I mentioned high availability. And the second reason that we might want to use multiple data centers is for performance reasons. So simply because of physics, if we have a user from Asia, it would make more sense to serve requests to that user from the Asia data center and not from the US data center, just because of, I don't know, the 200 milliseconds or so that it would take for the data to travel from the US to Asia. Okay, so that goes with performance reasons. And also here, just like nodes, data centers are created equal. We don't have the concept of master, slave, leader, follower, or whatever. They're all equal, and they can all serve requests. Okay, so maybe just a quick question, if you can answer in the chat window. What's your current NoSQL status? Are you running or using a NoSQL database? Yes, no. If you can just take a second and answer that in the chat window. Is this completely new to you? Are you already running a NoSQL database? Considering it? Thanks, Ron. Thanks, Shachar. Okay, so I see that for the people that answered are not running a NoSQL database. Okay, thank you for that. The next thing I want to talk about is some basic data modeling. And data modeling in NoSQL databases is quite different from relational databases. And this is a very high-level overview, but the main thing that I want you to understand from this slide is that typically when we think about relational databases and data modeling, we first of all think about the data, the different entities and the connections between them. And finally, we think about the queries and the application. That is the typical data modeling process. However, when we think about data modeling for NoSQL databases, we need to think about the application and the data at the very beginning. Okay, so when we create our data model, we need to think about what queries we're going to be running, and we have to create our data model according to that. And that's quite a big difference, and yeah, a conceptual difference that people have to get used to if they're coming from a relational database background. So some terms, I touched on them a bit before, but let's make sure we're all on the same page. So the first one is cluster. A cluster is a collection of nodes, and each cluster can have multiple key spaces. A key space is a collection of tables, and the main thing that is defined for a key space is the replication factor, or RF, which defines how many copies of each piece of data the database is going to hold. In a key space, we can have tables, one or more tables, and a table, just as you might think of it, has rows and columns. Okay, and at the lowest level, we have name value pairs. And when I showed you the example, I talked about SQL. SQL stands for Cassandra Query Language. It's similar to SQL, which you probably are familiar with, but there are some differences. And you can perform operations just as you might expect, read, write, delete, select, update, and so on. Okay, so here's an example of creating a key space. And in this case, the replication factor is defined as 3. Some common data types, I won't go over all of these, but like you might expect, these are the common data types that you can use with Cassandra and with ScyllaDB. You can also use collections, if that makes sense for your application, sets, lists, maps, and user-defined types. Each one has their pros and cons, but it's a bit out of scope. You can learn more about it on Scylla University or in the documentation. The partition key and the way data is partitioned is something I already showed you. And let's skip this because I have a lot I want to cover. Okay, so here is another lab that's way more elaborate than the previous lab I showed you. It talks about data modeling and gives examples of different primary keys, clustering keys, and so on. For the sake of time, I'm not going to do this lab. I will send you the link after the meetup is over, probably tomorrow, so you can do the lab on your own. Okay. Before I go to the read and write path, I do want to talk about an important concept in data modeling, which is the primary key, the partition key, and the clustering key. Okay, so it's highly important how we choose the partition key. And this lab goes over that and gives different examples, but I'll just touch on it briefly. So a primary key in ScyllaDB is one or more columns. And the primary key is basically 2 different keys. One is the partition key, and the second is the clustering key. Okay, the partition key, I talked about that before. That is one or more columns, and that determines how data is going to be partitioned on the different nodes. So if you remember, the database performs the hash function on the partition key, and that's how it knows which nodes are responsible for that piece of data. The clustering key is responsible for how that data is ordered within a given partition. Okay, so let's say we have, for example, the partition key is according to the state. Okay, no, that's a bad example. Let's say user ID, like I showed before. So a node might have the partition key as the user ID, but we might have multiple rows with the same user ID. Okay, and then the data in that, for those rows or that partition, would be ordered according to the clustering key. So let's say the clustering key would be the username. Okay, so we would have the partition key, user ID, and then the data for that specific user would be ordered according to the name. And making that selection is very important. We want to achieve high cardinality, which means an even distribution of the data among the different nodes. So we want to avoid a situation where we have either a large partition, which means one partition, one node that has a lot of data. So maybe I'll give an example of that. So let's say we're talking about users in the United States, and one of the columns is the state in the United States. So choosing the state as the partition key is probably not a good idea, because there are states like California, which have many people, and there are states that are very small, and they're not going to have many people. Okay, so that would not create an even distribution. That's not a good idea. Another thing that we want to strive for is to avoid hot partitions, meaning that we don't want a single node to be overloaded with a lot of requests, okay? So it can be either because it has more data, but it can also be because we access that node or that information more often. So when we create the data model, we have to think about those things. And if you go through this lab, it really covers all that I talked about, also the theory, but also it showed you some examples of how it looks in practice. Okay, I want to leave some time for questions, so let me go over the read and the write path. Okay, so the read and the write path, this is what actually happens under the hood in ScyllaDB or Apache Cassandra when we read or write data. Okay, so in this example, we have a cluster with 5 different nodes. The nodes are, we call them V, W, X, Y, and Z. And for this example, the replication factor is defined as 3, meaning that each piece of data is going to be replicated 3 times. And the consistency level is defined as quorum, meaning that for each request, it would be considered successful if 2 out of 3 of the replica nodes respond to the request.
A question. When you
Yes.
set the replication factor as 3,
Yeah.
do you have 3 copies of the data or 4? What the original plus 3 more?
So it's just 3.
Okay.
It's just 3, and let me go through this example, and I think it will be more clear. So in this example, our client, a client in a typical application, it would be a driver. Okay, a driver. We have drivers in different languages that can connect with a database, pretty much any language you want. So we have a driver, and it connects to one of the nodes. As I mentioned, all nodes are created equal, and it can connect to any one of the nodes. In this example, it connected to node V. And that means that for this specific query, node V will be designated as the coordinator node. Okay? And this is just for this specific query. Later,
But
a different...
Sorry. What is the mechanism that decides which node it needs to go to?
Okay, so that's a good question. It can be naive. It can be, in this example, just choose a random node. However, in an application, we have token-aware drivers. So the driver would know in advance which node holds the data, and it would ask that specific node to be the coordinator node. And in that way, we would save an extra hop and improve the performance. But that's a bit more advanced, okay? So
Okay, thanks.
In a naive way, we would just choose one of the nodes randomly, say node V, and the client wants to write a row. Let's call that row 1, just to simplify things. What the node does, node V, if you remember, it performs the consistent hash function on the partition key of the data 1, and it sees that 3 nodes are responsible for this piece of data, and these are the replica nodes W, X, and Z. Okay? The coordinator node, node V, passes this write along to those 3 nodes and tells them, please write that data. Now, these 3 nodes, we can see, add the data to their data storage. They write the data 1, and they send an ACK, acknowledgement, back to the coordinator node. Okay? Just in this example, we see that the acknowledgement from W and from Z pass back to V just fine. However, the acknowledgement from node X, for some reason, say there's a network failure, it doesn't pass to node V. Okay, so in this case, what do you think will happen? Will this be considered a successful write or not? You can write in the chat window, would this be successful or not?
Doesn't it depend on what command you give you choose, whether you want 1 or quorum?
Okay, any other ideas? Would this example, would the write be considered successful or not? Okay, so the correct answer is that in this specific example, the write would be considered successful, and the coordinator node V would return an acknowledgement back to the client. And the reason for that is because we define the consistency level to be quorum, meaning that 2 out of 3 nodes need to respond to the request. If in this exact same example, we would define the consistency level as all, that would mean that all 3 replica nodes need to acknowledge the request. In that case, node V would not return the success to the client, and the client would know that this request failed. Now, this brings probably a lot of questions, like what happens because the data was actually written. And that's a bit out of scope for this talk, but ScyllaDB has different mechanisms that are called anti-entropy mechanisms, and they make sure that the data is consistent, even if data is partially written to some nodes go down. So just for example, if this node has a hardware failure and it goes down, the database will still continue to function, and when the node goes back up, the other replica nodes will stream the data to the node that was down and update it with the data that it missed when it was down. So this is a repair mechanism, and it's something that's done asynchronously by the system, okay? So as you can imagine, this is quite complicated. It's a complicated piece of software, but again, this is something that's done under the hood, and as a user, you mostly don't have to worry about it. I'll show you another way to look at the write path, but this is in terms of storage. Okay, so ScyllaDB and Apache Cassandra work with something called an SS table. An SS table is a sorted string table. And when we write data to the database, what I'm showing you now is happening again under the hood. This is what's happening in the system. As the user, you don't have to worry about it. But when we write data, the data is written to a mem table, which exists in memory, and to a commit log, which is on the disk. Okay, and that means that the write is very, very fast. You simply write the data. You don't have to do anything. And it's written to memory and to the disk. Once the mem table becomes full, it's written as an SS table to the disk. Okay, and then a new mem table is created. Now, the reason we have the commit log is that for persistency, basically, if the system goes down, then we would lose all this data in memory, and then we would restore it from the disk because that's persistent. Okay. One interesting thing to know about might be a bit surprising, but the way ScyllaDB works and Apache Cassandra and some others is that data is immutable. And that means that when you delete data, it's not actually deleted. What happens is that it's written again and it's marked as deleted. Okay, and once we have multiple SS tables, there's a process that's called compaction, which gathers different SS tables and compacts them, discarding information that is no longer relevant. And then data is actually deleted. But when we perform a delete query, we actually write. It's actually a write query that marks that data as obsolete. So that's what happens with the write path. And here is another lab. And in this lab, this is the third lab. And as I've said, I'm going to send you the link for it. We run a 3-node cluster. And you can see an example of what happens when we have when we write and read data with different consistency levels, and we simulate a situation where some of the nodes in the cluster are unavailable. Okay, so because we're using Docker, it's very easy to simulate that. We just take down the node in Docker, and then we can see how Scylla would handle the queries when we have some nodes that are down. Okay, so that's the high availability lab. It gives you a pretty good understanding of replication factors, consistency levels, and high availability in general. We have an event called ScyllaDB Summit. It's happening next week. You can see the dates here. The event happens online and it's completely free. And you can Google Scylla Summit and find it, but there's also a link in the slides that I will send you, and you can register. The event covers different topics. Some of the things that I talked about. Also, it's going to have some hands-on labs, so I recommend you check that out. And here are some links for things that I mentioned: university.scylladb.com, the Learning and Training Center. Again, self-paced, free, online. You can just take different courses, different topics, whatever interests you whenever you have some free time. The community forum, so forum.scylladb.com. You can see what other people are doing with ScyllaDB. You can ask questions, you can share your use case. For example, if you're considering using ScyllaDB, you can ask the community to learn from their experience. There's also a Slack channel. You can find the link on our website. And this is the link to ScyllaDB Cloud. With ScyllaDB Cloud, you can start a trial cluster. You don't have to enter your credit card or anything like that. And you can simply start running Scylla and play around with it. Whoops, I didn't mean to do that. So we have like just a few minutes. Let's see if anyone has questions.
I have a question.
Sure.
Going back to the slide where you were showing 2 rings and 2 geographically different data centers, right?
Yeah.
Let's say I have a replication factor of 3.
Yeah.
I would like that replication to be in both data centers. So if one completely goes down, the other will be able to serve that. How do you accomplish that?
So ScyllaDB is topology aware, and it's aware of the different data centers and of even of racks within the data center. So that's something that you can define when you define your topology and the data centers. There is something that's called, I think it's called replication strategy, but I'm not sure. Anyway, there's something that you can define, topology aware replication strategy or something like that. And
Let me
then
ask you the question differently.
Okay.
In this example, will
Yeah.
both of the data on both data centers will be equivalent?
So that's up to you. You can look at it as
Okay.
one cluster where the data will be replicated to the different nodes, regardless of the data center. But that probably, in many cases, would not work very well. So you can look at the two data centers separately, where the data will be replicated to each data center specifically, and then it can be replicated between the two data centers asynchronously.
Okay.
So you can define that. That's up to you as a user, and depending on your use case, the amount of data centers that you have, and so on. And by the way, that question also, I talked about Apache Cassandra, but there's also ScyllaDB also is a drop-in replacement for DynamoDB. And with DynamoDB, I don't know if anyone here uses it. It's quite a popular database from Amazon. And there are significant costs for networking. So for replication across different data centers or within different zones in a data center, there are quite some significant costs. And by changing to ScyllaDB, people get a very big reduction in costs, up to ×10 or even more, because they don't have to worry about that. And also, of course, many users are switching from DynamoDB to Scylla because they don't have the vendor lock-in. So big companies are not crazy to be tied to one specific vendor, Amazon in this case. By switching to ScyllaDB, they can run ScyllaDB either on AWS, but also on Azure or GCP or even on their own machines. So that's another important point. Maybe one last question.
When will you not choose Scylla as your DB?
That's a good question.
Can you hear me?
No?
Yeah, maybe he went down.
Yeah, I think I went down. I don't know why.
He's not running ScyllaDB, that's why.
Yeah.
Yes. Someone listen to me. So yeah, I think I missed your answer. Excellent.
And he's back.
Okay, sorry about that. I hope you can hear me now.
Yes.
So yeah, I'm usually running on Linux, and just for this meetup, I started Windows and it just crashed. So anyway, the question was, when would I not use ScyllaDB? And that's a good question. The answer is if I require very strong consistency, as in ACID consistency, maybe ScyllaDB would not be a great choice. If performance is not that important to me, so if I don't care about how fast and I don't have queries that need to be run in real time, then maybe ScyllaDB is not a good choice for me. And also if I'm running a small amount of data and I don't expect it to go up. Okay, so if I'm just running, I don't know, an application with a few thousand users and I don't expect it to go way higher, then maybe that's not a good use case for ScyllaDB. There's a lot more of information about that on our website and on the forum, because that's a good question that comes up.
Oh, maybe you can send this in the email that you sent. Are there any like white papers that will show the path to go from a SQL database to a NoSQL database?
Yeah, so I will add a link to that and also to the ScyllaDB sweet spot those are two things I will add with the slides and send you all of that by email.
Thank you.
My email is guy@ScyllaDB.com, so feel free to reach out, ask questions, and I hope you learned something. Thank you everyone for joining.